Yeah, thank you for the introduction, and thank you to the organizers, not just for letting me speak right after this incredible presentation, but also thank you, the entire team, for putting together another fantastic Big Sick. I enjoyed it thoroughly the last couple of days, and I'm sure I'll enjoy the rest of it. So, after the last Big Sick, I was talking to Anders and Daniel, and they asked me, wouldn't you want to do like a longer presentation? We usually do the shorter industry pitch about something that's new and that's upcoming. And they asked me, could you probably do something like real nerdy about something technical, but still around resuscitation? So like, probably think about something. I said yes right away because I think it's fun to present here at the Big Sick, one of my favorite conferences in the year. And then we thought a little bit, what about should the presentation be? And we settled on defibrillation, like John just pointed out. And we called the presentation Black Magic or Science. When I say we, shout out to one of my colleagues, Julian, who helped me put together the slides. They were finished last evening, so they could be uploaded on time. And this is the first time we're using them. Why Black Magic? Because defibrillation or electricity in general is something that's a little bit hard to grasp. In the back there, right next to us, the Hamilton guys with the ventilator. So their machine makes a noise, we hear it, we see it moving air. When it's connected to a patient, we see the chest rising. With electricity, we or all of you have to kind of believe that the device does something that's useful. Like it happens inside, electricity, we can't smell it, we can't see it, we can't touch it, at least we shouldn't really touch it. We know that's kind of dangerous. So I'll give you some insight of what's happening. I'll also give you some insights from our perspective, what makes defibrillation, or what makes a defibrillation a good defibrillation, and give you some outlook what might come in the future. What I want to start with is one thing. I was asked to give that kind of nerdy look into that, and we've put together kind of the most important formulas that you need to know to understand defibrillation. So I think for the next 17 and a half minutes, we'll just go over those. And by the end of that, you'll probably be able to pass your 10th grade physics exam again. It's kind of funny because like I thought, like, how can I make it as nerdy as possible? And I thought I'll put a picture in here of this world-renowned theoretical physicist. And as much as it actually looks super complex, if you see in the top-hand corner, we'll actually cover on that. U equals R times I. Is actually one of the easiest things to remember because it refers to a canton here in Switzerland called Uri. You don't have to remember any of those. The presentation will actually go the complete other way, and I haven't seen Ross yet, but I think there's only 2 slides that have text on them. The others are pictures. So why pictures? Because I think it's probably going to be the easiest way for you to remember what defibrillation is about. And for this very first example, I put the knot in here. And there's one thing that I want to start with, which is kind of intriguing because I started in EMS in 2002. We've all read the resuscitation guidelines for the last decades, for the last years at least. And we still measure defibrillation in joule. It's in the guidelines that it's probably not the right way to measure it. And there is a full-blown reason behind that. And that is, joule is actually a scientific unit, a value that has a time component to that. And I think around about 10 years ago, I started making the joke, if you want to shock yourself with 10,000 joules, you might as well lick a 9-volt battery for long enough. And to my extreme surprise, there was no picture on the internet where somebody was licking a 9-volt battery. So this is obviously AI generated. I don't know whether anybody has ever tried that. And because this is a scientific conference, I obviously checked, and 10,000 is actually an underestimation. If you lick it for long enough, and if the battery is fully charged at the beginning, it's actually 18,000 joules. So obviously this is way above what we are used to, and that is because it has this time component. So nobody would think a defibrillation impulse takes an hour. So what is the difference kind of if we use something that is really slow? Like if I was to like clap my hands like this, might be the same energy that I apply as I do like this. So basically this is the idea behind a defibrillation impulse. It's something harsh, it's something quick, something that happens in a very short period of time. Now, an hour is a very long period of time if we compare that to a defibrillation impulse, and modern impulses are probably no shorter than 8 milliseconds and not a whole lot longer than maybe 12, 13, 14 milliseconds. So a fraction of a second, so that we have this very harsh moment where we deploy this energy to actually defibrillate the heart rate, the ventricular fibrillation. So then there are a couple of other values that come across when we talk about electricity. And one of them is voltage. Voltage is something that we're quite used to. If we go again back to the battery, that was a 9-volt battery, like our standard AA battery, 1.5 volts. If we charge our phones here, USB is 5 volts, and then a regular power outlet here at least is 230 volts. As I learned yesterday, the 11th province of Canada in the south, 115 volts. So kind of the range that we are used to, 1.55, maybe 115, 230 volts. Defibrillators use slightly more, in the thousands, maybe around 1,500, 1,800 for smaller public access AEDs. Professional ALS devices maybe in the mid-2000s. Our ALS defibrillators that you see in the back use 3,500 volts or 3,400 inside in the capacitor and 3,200 at the patches to make it a bit more nerdy. So this is what we use to transport energy. So voltage by itself doesn't do a whole lot, and I don't know whom of you have been to a technical museum recently or like some science exhibition. This here is a very old picture of the Professor Tesla, not the vehicle and not the guy that we probably think of if we hear Tesla. It's also the reason why it's black and white. So with voltage, you can create lightning that you can actually touch and it barely even tingles. So voltage wouldn't be suitable for a defibrillation. Voltage is kind of a vehicle that we use to transport energy. And one other example for that would be like overland power lines, like those really big ones that are on the mast. They use hundreds and thousands of volts because that actually makes it possible for those wires. They're not really wires, but like for the picture, they can be wires to transport large amounts of electricity for long distances with as little loss as possible. So voltage alone wouldn't really defibrillate. Still, I said at the beginning, maybe don't touch it, so also don't touch a power outlet. Probably safer not to, but an important vehicle for us to get actually to where we want to be, and that's defibrillation. And that then leads me to another value, and that's where it gets really interesting. That's current measured in ampere and amps. So if we have enough of that, we can, for example, melt metal. That's why welding is one of the examples here. Again, a little bit of a comparison. If you ever worked on cars and you probably used a spanner that wasn't insulated and you replace the battery, if you put a spanner between the plus and the minus battery of a car, you can actually melt that spanner. Same reason if we look at older light bulbs, why that wire is actually glowing and emitting light, it's current. Or something that is a lot more often used by us in our medical profession, and that is transcutaneous pacing. So if you think about pacing a patient, you have a bradycardic patient, and you have tried everything that you thought at first, like atropine and whatever, and then you thought electricity might be able to help, and you apply patches, and then you set the frequency to, let's say, 80 or 100, and then you slightly increase the current. And in the books, it probably says around 50 milliamps you will get capture. I think it's more maybe around 80 to 100. So 0.1 amp, you will get capture. So less than 1 amp in a pacemaker scenario gets you capture, so it gets the heart to react. And you see the more current you give, the more the heart reacts. And that's already pointing into this direction. Again, to put it in comparison with regular defibrillators, 10 amps is kind of the minimum that you would see. An ALS device probably, again, above 15, 20, 25, 24. Varies a little bit about how the technology is. And because the standardization committees deem that as a very important information for you to have, if you look into instructions for use, somewhere in the back of the pages, you will actually see how much current the device is able to produce and to induce the electrical field with, because this is something that is required in the DIN ISO standard 60601-1- and I forgot the number. So this is for all the medical products, and there's the standards, and they're required to have that. So if you are interested to see how much current the device emits that you use in your daily practice, just look at the user manual. The majority of them are available online, and you'll see it. So current together with voltage doesn't just help us to weld, because we are not here to work on cars. We're here to improve our patient care. But the electrical field that induces is very, very similar to an electric magnet. And how does that now translate to patient care? And we brought this slide to just reiterate that obviously this is kind of where the heart sits, and I think this is something that I've seen a little bit as a theme going through this conference, that physiology matters. We have to keep in mind what we are dealing with, in this case the heart muscle, that it matters where it sits and maybe even the orientation. So this just as a quick reminder, obviously this was a nice and healthily beating heart. Unfortunately not able to pump any blood, but that is just due to the lack of time on the computer, I'd say. And then obviously we all know that there's a conductive system around, like where we have a sinus node, an AV node, and so on, all the way down to the myocardium cells that have a more positive and a more negative side. And that comes into play if things don't go that well. And I am aware that this is not what VF looks like. The majority of you have probably seen that in an open chest scenario, but we didn't have a much better way of making that look like it is no longer beating, but fibrillating. So this is obviously a state that's not ideal, and we've heard in various other talks what we can do. So if we do everything perfectly and we do perfect chest compression and might even alter our chest compression position and so on, at one point we want to defibrillate, and then we have to introduce patches. They're also not quite to scale, like they look a little bit small if I compare them to like the size of a rib here. But what's important, and what's the important takeaway message from that, is that pad placement matters. So that would be kind of ideal if we're keeping in mind where the heart is, and that we put the two pads in the right position. And with a sternal position, that seems to go fairly well. That is very easy accessible, but the lateral one seems to be a bit of a challenge. And last weekend, I was at a emergency medicine conference up in northern Germany, and a couple of other people that are here today have been at the same conference, and we've seen a small study where they looked at pad placement. And while it's like 90% or something with a sternal pad, that's correct, I think 65 of them, of the lateral ones, were placed in the wrong position. And that's from my clinical experience. When I arrive as a second vehicle, it's quite often like the sternum one moves further down, and then the second one is like way far towards the middle, and it almost looks like it's there to stimulate the diaphragm. I don't know whether that's approach for weight loss, but definitely not ideal for defibrillation. So the position does matter, and I understand that it's sometimes a little bit difficult at the beginning. So as long as the pads are in an area so that the electrical field that is induced by the voltage and the current that I've just shown you guys before, the heart's in the middle, then actually defibrillation has a good chance. And the same thing is obviously for double sequential defibrillation. So whenever somebody approaches us from our company and asks like, oh, what about the double sequential defibrillation? I feel the need to tell people that the positioning of the pads does matter, and that the vector definitely plays a role. But at the same time, I'm a big fan of double sequential defibrillation. And how couldn't I? Because, I mean, it would make my commercial role a whole lot easier if all of a sudden all ambulances have 2 defibrillators. I mean, that's fantastic. And I encourage everybody, if you want to do like a triple external defibrillation trial, go for it. Like, this is definitely something worth investigating. But if you do, and jokes aside, if you do double sequential external defibrillation, I put together a couple of how-tos, just things that we've seen talking to different people in different countries, different systems. You might want to consider using 2 identical defibrillators. Like I pointed out before, there's a bit of a range of voltages. Some of them might use a slightly lower voltage, and then they're also insulated against that lower voltage. So if you combine that with one of ours, you might risk to damage the other one, which again, from my commercial perspective, is probably not that bad, because then you're in the need to buy another one. But just for you to keep your equipment, that's probably something to consider. We have done thorough testing, like combining the Corpuls 3 and the Corpuls 1, like in various, like 2 Corpuls 3, 2 Corpuls 1, and any kind of mixtures. That works perfectly fine with our devices. They do have a special function that's called auto sync, which we would recommend to deactivate if you want to do double sequential external defibrillation, because then you get an immediate shock release. And something to keep in mind, is devices measure the transthoracic impedance to identify how much they need to charge their capacitors. And if you have 2 devices trying to do that at the same time, they might interfere with each other. So you might get a reading of impedance high or impedance low, but that is to be neglected. The last how-to is something, because a lot of people, when they've had a patient that qualified for double sequential external defibrillation, like we had in the workshop yesterday, and decided to do so, then they come to us and it's like, oh, can you have a look at our data, because we want to know whether it worked and how much was the time in between and so on. That's every time, or not every time, but very often when it's being applied, they actually want to look at it, what happened, and therefore it's extremely helpful if you store your data. And pretty much every large manufacturer has cloud data storage available for the defibrillators, and then you can actually find the data easily, and you don't have to chase which defibrillator was the first one that was attached, and where's that memory card, and how can we look at this to compare that. So if you think you're going to use that and you want to look at your data in the future to see how it worked, then I'd highly recommend for you to store it. One thing, and that's I want to take us back just to see what other opportunities there are. David from Melbourne, Australia, gave this presentation last year about a trial that they started there, and they wanted to alter, or they wanted to try whether they can alter the transthoracic impedance. The impedance kind of being something that is limiting our, oh, that actually, can you see that? Yeah. No, for me here it looks like a laser pointer, but there it's a mouse. But I told the guys yesterday I'm not going to use the laser pointer, and now I'm actually doing it. But like you see here on the left-hand side, that barrel that says capacitor on it, kind of like here compared to a water tank. So this is where our charge goes into, and then we have that full, and then we want a controlled release of the current, like we see here in the pipe, and then in the middle there where it says patient impedance, the pipe all of a sudden gets smaller. And the idea behind the trial that the guys in Victoria, in Melbourne did, was to compress or press onto the pads, which I think is quite quite a bold move, but I know, and we heard it here last year, that they did have a sophisticated safety protocol in place. So they used standard nitrile gloves, I believe, and then pressed onto the pads, which are nicely placed here in this case, to ensure really good contact of the pads, but also introduce pressure onto the lungs, because the lungs are full of air, and air is a perfect insulator. So the more air they pressed out, the better the impedance got. And as an effect, the lower the impedance is, like we saw before with that pipe, the more current can flow. So I borrowed one of their result slides. So basically across all different BMI levels, they were able to show that when they introduced pressure, they could lower the impedance and as an effect, increase the current that was deployed. Unfortunately, somebody didn't quite follow the safety protocol, and I believe somebody used this technique in a wet scenario on a boat, on an aluminium boat, and what wasn't supposed to happen happened and got defibrillated, and they had to finish the trial early, because I think they would have been able to produce some really insanely cool numbers. But I think this already shows us lower impedance gets us higher current, which seems to be good. And this is what I kind of put on that intermediate summary page. So all we need is current. I remember a very good article titled "All We Need Is Flow" around use of mechanical CPR, and I thought this pretty much fits. So it seems that precisely what we need is a short enough time frame so that we have this high impact, sufficient voltage to carry enough energy, enough average current. Average current, it's kind of when you look at like all the different impulses. I don't think like the shape, whether it's more like a parallelogram or something like this, I don't think that has any effect, but a high enough average current that's as stable as it can possibly be. Therefore, we need regulation parts that are on a PCB to actually guide that current, and then the correct pad placement. So that's basically the most important ingredients that already lead us to a successful defibrillation. And I said I will show you a small outlook what one may come up with, and we've done this kind of research for the last, I'd say, 15 years now. It was kind of a side research with mechanical chest compression at first, and then turned into more around pacemakers and defibrillators. And we found a way how we can build a high voltage unit that is no heavier, no bigger, and still fits in a portable defibrillator, but releases a higher mean current, and designed a multi-center study. This is the study design that I brought you here, in 4 regions in Germany, led by the city of Cologne, where I went to university. So obviously contacts help to put something like this in place. You see here different population densities in the different study centers, different areas, and the incidence per year. Here's the out-of-hospital cardiac arrest with VF as an initial rhythm. So this is where this calculation leads to. So it's not that there's a very, very little amount of cardiac arrests, but it's just the VF cases. And here you see the devices that have been deployed. So we built those devices under the medical device directive. So they're actually approved medical devices with that alternative high voltage unit. We designed the study so that it includes 265 patients per year. We've just finished the data collection, and we're able to include a little over 1,000 patients. So that's also why the data, our processing of the data takes a little bit longer, while the annotation, I think, is well on its way. What we looked as the endpoints, obviously termination of VF-VT. This is what a defibrillation impulse does. It does fibrillation first, and then there is no more. We also looked at the return of an organized rhythm, number of shocks to get there, the patient impedance that I mentioned earlier, the energy that was delivered per shock, and of course the average current in the positive and negative phase. There's kind of an 80-20 split between the positive and the negative. And those were the hypotheses that we went in there, and PMCF is something that people that work in the medical device industry are very familiar with. It's what companies like ours are required to do. It's post-market clinical follow-up, which basically ensures that the devices do what we claim they are supposed to be doing. So 2 non-inferiority claims, that the standard impulse is no worse than the literature data, as well as the modified one is no worse. And then the interesting one, the third hypothesis that's on here, it's basically, again, non-inferiority, but is a theoretical better defibrillation impulse actually capable of bringing or terminating more VF and getting more return of organized rhythm than a standard impulse. And as much as I'm not fully involved in the trial, I know who does it, and it's an incredibly good team. And I did have a bit of a look, and I'm really, really looking forward to that data hopefully being available around the European Resuscitation Council Congress later in this year. So stay tuned. I think this is going to be interesting. And I think that is pretty much on time. That is the last slide. And this QR code will basically show you something that we've done a little bit over half a year ago. Bit of a fun video of the Zermatt guys here using the equipment in a more unique scenario on the mountain, and including crevasses and so on. Thank you very much.
Thank you. That was